Assalamualaikum and hi. So this is the lecture for frequency response design using lead compensator. There are a few advantages of using lead compensator for improving the transient response through lead compensator and also improving the steady state error through lead compensator. So besides these advantages of improving these two transient response and steady state error, there are other advantages to increase gain at lower frequency, to improve the system stability. Besides they improve the steady state error as mentioned before, improve gain margin at the gain crossover frequency and improve the speed response based on this transient response, either peak time or settling time. So this is the lead compensator transfer function. So this is the compensator transfer function. KC is the overall gain, and this is for lead compensator, while this is for lag compensator. So in this case, alpha is equal to beta. So we arrange this transfer function of alpha and beta into this one, and the compensator gain is equal to KC lead multiplied with KC lag, so it becomes 1. In this case, this is beta. KC lead is equal to beta, KC lag is equal to 1 over beta. So for step 1, we need to determine the damping ratio from percent of overshoot. And based on this damping ratio, we determine the required bandwidth frequency using the damping ratio and also the value of either peak time or settling time. If you are given the settling time as the design requirement, you use this formula to determine the bandwidth frequency together with the damping ratio value. Otherwise, if you are given peak time in the question, you use this formula together with the damping ratio value to determine the required bandwidth frequency. In step 2, we need to determine the unknown gain K from the static error constant to satisfy the steady state error requirement. Usually, the static error constant will be given in the question, and using that static error value, we determine the unknown gain from the given transfer function. In step 3, we draw the dot plot of magnitude and phase. So from this transfer function in S domain, we convert the transfer function in frequency domain by replacing S with J omega. And then we construct the Bott table before we draw the Bott plot for magnitude and phase using semi-log graph paper. So for step 5, we calculate the desired phase margin from percent of overshoot or damping ratio. So from percent overshoot, in step 1, you can determine the damping ratio value, and using the damping ratio value, you can determine the required phase margin, or we call it as desired phase margin. So using this formula. So in step 5, we determine a new phase margin frequency. In this case, we label as omega PM prime. The formula is 0.8 multiplied with required bandwidth frequency that we determine in step 1. So this is the omega PM prime in radian per second. In step 3, we determine the additional amount of required phase lead angle. So this is based on correction factor given in the question. For example, this one is 5 degree. So using this value of omega PM prime, in step 6, we need to use this value, refer to the phase plot to determine the phase value. So in this case, we label as phi m omega PM prime. So we determine the phase value, and then using this value, we determine the phase margin of omega PM prime, 180 degree plus phase margin omega PM prime. And the last one, we determine the required phase lead angle, or we label as phi max. So phi max is equal to desired phase margin from step 4 minus PM omega PM prime from step 6b plus the correction factor given in the question. So it will be in the range of 5 until 12 degree. So check the question. what is the value of correction factor. So we continue in the next video from step 7. Thank you very much.